Hi, this video is going to cover the Alkane section of Module 4. We're going to look at the properties of alkanes, their shape, the fact they've got sigma bonds, the boiling points. We're going to look at the reactions and why they're not actually that reactive. And the two reactions we're going to concentrate on are going to be combustion and free radical substitution. So, first up, if we look at the properties, and we take just an ethane molecule, what's this made up of is a whole series of, well, we've got one carbon-carbon bond and one carbon to hydrogen bond. And all hydrocarbons and alkanes have these bonds, and these bonds only in them. When we add other functional groups, we start to get different bonds, but then they stop really being alkanes outright. So both of these are what we call sigma bonds, and now these are very, very strong bonds, so difficult to break down. So that's one of the reasons why alkanes aren't very reactive. Also, the electron negativities of carbon and hydrogen are very, very similar. So the electrons sit pretty much in the middle on that bond. So there's no dipoles forming. So again, that makes them not very reactive as well. So no dipole, very strong bonds mean alkanes are unreactive. Now the shape of this bond, if we just look at this carbon here and have a look, although I've drawn it here as if it's square planar, it's actually got a 3D structure. Now there are 4 bonded pairs and 0 lone pairs of electrons around that carbon, which makes it tetrahedral. So we'd have our carbon to a hydrogen. I'm going to put this way my CH3 group, that's coming off that way, then coming out towards me in this 3D structure, I'll have a hydrogen, and then going back I'll have a hydrogen as well, with a bond angle of 109.5 degrees. So this would be what this would look like. Obviously this CH3 as well would be tetrahedral in structure, so that would have a H going up. So it would look like that as well. So it's got a 3D structure. Boiling points then of these, and firstly, boiling points of alkanes increase as they get bigger. And this is down to the fact that as they get bigger, they get more electrons. So 10 electrons there, 18 electrons there, 26 electrons there. So we're getting more and more electrons, and that means if we get more electrons, we get stronger London dispersion forces. Great. So these two CH4 molecules will be less attracted to each other than two C3H molecules. You've got to overcome that. The other thing we look at boiling point is branched versus unbranched. So an unbranched alkane, if we take a nice long chain, we've got there a hexane molecule. I'm going to do this skeletal just to represent it better. And then let's take a branched one. So both of these have got the same molecular formula. They're both C6H14. Here we've got 2,3-dimethyl butane there. And so what happens with the hexane? They've both got the same number of electrons, so you'd expect the forces in between them to be exactly the same. But what this hexane can do is layer very, very neatly. And what that means, if it can get into this kind of layer sort of pattern, is it can have lots and lots of interactions with neighbouring molecules. So lots and lots of London dispersion forces, because it's nice and neatly layered. Whereas this branch chain we've got here can't get quite into the same layers. So we'll have some London dispersion forces connecting the two molecules and holding them together, but not as many as the straight chain. So the straight chain will have a higher boiling point. Okay, next up, we're going to look at the reactions. So when we looked earlier, we talked about that sigma bond and it being very difficult to break down. And so our alkane, here we've got ethane, made up of sigma bonds, very, very strong, difficult to break down, so nice and stable, and also no dipoles, so nothing for it to be attracted to. So maybe there is something that will be reactive, but it won't attract the ethane. Ethane will stay as it is, so it won't get over to anything that does want to react. The sigma bond freely rotates, so we can get free rotation of this. So what I'm going to do here is just change the colours of these hydrogens just to emphasise this. If we put that one as green, keep that one as black, and that one as red, this bond can rotate, and any of the bonds can rotate. So you could get the carbons moving around, so the hydrogen could go to there, this hydrogen can move to there, and so forth. They can go into any position that you want, because the sigma bond can rotate completely. When we look at alkenes, you'll see that the pi bond stops rotation from occurring, but the sigma bond can rotate completely. So combustion next, and we have two types. We have complete and incomplete, and they're very, very similar. The only difference is the product. In complete combustion, we'll take our alkane, sticking with, it's not great there, so try that out a bit. Sticking with ethane, react it with oxygen, because that's what combustion is. Let's set a light in an oxygen environment, and it'll go to carbon dioxide and H2O. So in complete, we get CO2. Now, just balance this quickly. We've got 2 carbons here, so I need 2 there, 6 hydrogens, 3 there. So I've got 7 oxygens on this side, so that's 3.5. So in incomplete, if we take the same one, and now this happens when we lack oxygen, so there's not a lot of oxygen in the environment, we get instead carbon monoxide forming and H2O. So the same balancing numbers go on this side, 2 and 3, because we've got 2 carbons, 6 hydrogens, but now we've got less oxygen here. We've only got 5, so we get 2.5 oxygens there, so less oxygen on this side. And that's combustion, so complete, incomplete, and the big difference is, or the only difference, is this carbon dioxide, this carbon monoxide, which causes less oxygen. Next, free radical substitution. Okay, in this we're going to have 3 steps. First of all, actually we'll do the overall reaction. So let's take C2H6 plus Cl2 is going to go to C2H5Cl and HCl. So, first step we call the initiation. And what happens in the initiation step is our chlorine homolytically splits into 2 chlorine free radicals, and it does this in the presence of UV light. So UV light comes down, shines on the Cl2, it splits it evenly. So the 2 electrons in the bonds between the chlorine, one goes to one chlorine, one goes to the other. So now we've got an unpaired electron on each, makes it quite reactive. So the next step is known as the propagation, and there's a few stages in the propagation step. This chlorine free radical can now react with our ethane. And that is going to form our ethyl free radical and HCl. So we've got a hydrogen taken away from the chlorine, that gives us our HCl. Now this is then free to react with all sorts of other things. In this case, just to demonstrate, I'm going to do it with the chlorine. So early on we had chlorine, there'll be plenty of that around. So just because one's split up here doesn't mean there aren't other chlorine molecules around as well for the ethyl free radical to react with. And that forms our free radical back again. So our initial one that was formed up here, sorry. So this can then continue and go on and on and on again. So propagate again. And our C2H5Cl. And this will go on and on and on again till either we run out of molecules or we hit a termination step. And there are lots of different termination steps we can have. But the common ones here are if two chlorine free radicals can come along and combine back to form a chlorine. Or two ethyl free radicals can do the same to form butane, or a chlorine free radical and an ethyl free radical can combine to form chloroethane. So we've got several termination steps. There are lots and lots of other steps though that can be involved in this, and lots of other products, because this C4H10 doesn't disappear. This then could react with a chlorine free radical to form C4H9 free radical, and then that reacts and carry on going, and we can get lots and lots and lots of different products. Which is why if you're trying to make chloroethane, this isn't an ideal reaction to do this with, because you get lots and lots of other products forming in it. That is the alkane section of Module 4.